Okay, today is lecture 9. So welcome to lecture 9 of electrical machines course. And we are continuing the transformers. Okay. So transformers, last class we discussed an ideal transformer where we neglected the losses and without considering the resistance of the winding and without considering the leakage flux, and also we have neglected the loss in the magnetic core, that is the magnetic loss or core loss we call it, right? Or sometimes we call it iron loss. And we know the magnetic loss has two components. One is eddy current loss and hysteresis loss. So later in this lecture we'll discuss how we can consider in a practical transformer, how we can consider those losses and find out the equivalent circuit. And also we have seen the equivalent circuit of the transformer in case of ideal transformer. Simply just it is just two windings and with a core, right? So just like this we have seen in the last class, nothing else, no resistance, no inductance, nothing. These two lines indicate the core, right? The core of the transformer. Okay. This is all we are discussing. Already you have seen these equations. The ampere turn or mmf at primary side will be equal to the secondary side, and from which we found I2 by I1 equal to N1 by N2. This is the turns ratio equal to A. And the volt ampere or the apparent power also will be equal from both the side because the losses are zero in the transformer. This is the ideal transformer, right? And if we consider phi equal to phi m sine omega t, then your induced EMF will be this, and obviously found from that the RMS value of the induced EMF and both the side, primary side and the secondary side. And then by taking the ratio of V1 by V2, we know N1 by N2 is equal to V1 by V2, and hence it will be equal to E1 by E2 because there is no voltage drop because we are neglecting the resistance here, right, in the winding. And V1 I1 star is your complex power that will be also equal at the both end of the transformer, input side and output. And we know this is the phasor representation. And if the load that is connected here, this is Z2, if it is transferred to the primary side, suppose, no, this is, yes, if it is transferred to the primary side, I can write this as A square Z2, okay. So that means the secondary side impedance, any impedance, if we'll transform this any impedance from the secondary side to primary side, we have to multiply A square. So A is nothing but it is N1 by N2, right? A is nothing but it is equal to N1 by N2. So already we have seen how to derive this. Similarly here, your Z1, this impedance is transformed from primary side to secondary side. When it is transformed, we can write Z1s by A square. Okay. Okay. Up to this we have discussed in the last class, and today we'll see transformer polarity first, then we'll talk about little bit about ratings. Then we'll go ahead with a practical transformer. The discussion will continue with a practical transformer. So what do we mean by the polarity of a transformer? So polarity, we have two windings, right? Here you can see we have one winding which is connected to the source. We call it primary winding. And we have another winding which is connected to load. It is connected to load is known as the secondary winding, right? So either of the winding can be made primary or secondary. Okay. based on the connection. Where you connect the input, that will become the primary winding, and where you connect the load, that will be connected, that will be known as the secondary winding, right? Okay. Now the polarity means we'll mark the polarity in these two windings based on the polarity of the induced EMF in these two windings. I will say, so suppose at a particular instance, suppose this is your waveform of E1, right? Suppose at a particular instance of E1, let us say, and this E1 is suppose at this instant, at E1, let us say this part is positive and this is negative. This is with respect to the other side, it is giving a positive value. Then under that condition, at the secondary side, if where it will be the positive part, that means where it will be the positive side with respect to the other side, we'll mark that at positive. Let us say at the secondary winding, the positive part is here and the negative part will be here. Then I will mark it this positive and this is negative for that particular instance. Okay. Now hence I can mark two dotted terminals at the windings of the transformers. That means the dotted terminal indicates that at a particular instance, the polarity of these two windings are same. Okay, that means at a particular instance, if it is positive, it will also, the dotted terminal of the secondary winding will also be positive. And if it is negative, then this will also be negative because every cycle it will change, right? So it will also be negative. Okay. So that is the indication of polarity. Now the question is how the voltage will induced in the secondary side so that the flux produced in this coil will oppose the flux produced by the primary coil. So under no load condition, we know there will be no flux produced by the secondary winding because there will be no current in the secondary winding, right? Now when the load is connected, the current starts flowing in this circuit in the secondary side, then what will happen? Then your flux which will be producing in the secondary side, that will oppose the flux due to the primary side. We know this is the Lenz's law, right? So therefore, then what direction the current should flow? Okay, so now if the current will flow in this direction, then it will produce an opposing flux, right, to phi, right? So when it will produce an opposing flux, that means your current is flowing in this direction, then obviously this will be positive, this will be negative, and hence I can mark the dotted terminal here. So therefore, in general, in a transformer, we can conclude how we can mark the polarity. In your lab also, you will do the experiment how you can mark the polarity. Okay. So you can see here, this is the equivalent circuit of the transformer, ideal transformer, right? And now, so the dotted terminal marked in such a way in these two terminals, suppose this is your primary winding which is connected with a source. Now I can say that if the current is entering to the dotted terminal in the primary winding, then the current should leave the dotted terminal in the secondary winding if the load is connected here. Okay. So this says the polarity, like by principle, the principle of operation of transformer, it says when the current is entering at the dotted terminal of the primary winding, the current should enter at the dotted terminal of the secondary winding, right? And in the other cycle, suppose the current direction changes, it is leaving the dotted terminal at the primary side, then here it will enter the dotted terminal at the secondary side. Okay, so just opposite. Okay, then in the next cycle again it will become, the current direction will change, again it will leave the dotted terminal. So this is the principle of the transformer polarity, right? You will also in the experiment we have to find the polarity of the transformer in the transformer open circuit set test and short circuit test. Also you need to find that. So we will do that experiment. Okay. Okay, now this is all about the polarity. Now we'll talk about the ratings of the transformer. So what is the rating of a transformer? So if we'll see a transformer, whenever you will have an opportunity to go to a power transformer, go near to the power transformer, there is a nameplate rating. So you will see there is a nameplate, and in that nameplate you will see some of the values are written. Okay, what are the values mentioned generally in the nameplate? So the nameplate of a transformer provides information on the apparent power and the voltage handling capacity. That means the only information we get here in the nameplate, that is, this is for ideal transformer we are talking, not for practical transformer. So for practical transformer, other things are also mentioned like percentage reactance, percentage impedance, everything. So here the apparent power is VI, right? That is in MVA or kVA, whatever. If it is a small transformer, then it is mentioned in kVA, or it is very small, it is mentioned in VA, right? So apparent power unit is kVA or MVA or VA, volt ampere. So many of you in the quiz, you have mentioned watt. It is not watt, right? So it is volt ampere or MVA, megavolt ampere. Like if you'll go to our transformer here in main substation, you'll find it is 5 MVA, right? 5 MVA means it is the volt ampere, right? Sorry, it is MVA. Okay, so volt ampere, right? Then it gives the information about the voltage handling capacity. That means the voltage at one side and voltage at the other side. If it is a step up transformer, the higher side voltage, the high voltage winding voltage rating, and the low voltage side voltage rating, right? So if you are making it now, you are making it a step up transformer, then your high voltage winding will be connected to the load side, right? And the primary, the low voltage winding will be connected to the voltage source, right? That will give us a step up transformer. And if you want to make it step down transformer, then obviously the high voltage side will be connected to source side and the low voltage side will be connected to load side. Okay. So here we'll find only step down transformers. In IIT Patna we have many step down transformers. Like in the main substation you'll find 33 kV by 11 kV, right? So that is high voltage side is connected to the source and 11 kV side is connected to the load side. And then again the 11 kV is transformed using the step down transformers. So 11 kV to 440 volt. We have many substations around the campus. Okay. So now from the nameplate data, suppose we have a rating given here, a transformer having 5 kVA volt ampere apparent power rating, and the voltage rating is given 500 is to 250 volt, and it is obviously a step down transformer. Then what we'll conclude from this is the full load nominal power rating of the transformer is 5 kVA, right? Full load, right? So under full load, the transformer can give maximum up to 5 kVA if the losses are not there. In other words, the transformer can deliver 5 kVA on a continuous basis. Since it is a step down transformer, the nominal voltage V1 will be 500 volt. Okay. And the secondary voltage V2 will be 250 volt. Then if we'll find the current, we can find easily the current from here because the voltage VA is given apparent power. So you can just divide the voltage with the apparent power, you'll find the current. So here the nominal magnitudes of the primary and secondary currents under full load will be I1 will be 5000 by 500. It will be 10 ampere in the primary side. This is your full load current. Okay. Full load current. And in the secondary side, the full load current will be 5000 by 250, it will be 20 ampere. And the transformation ratio we can find easily because this is ideal transformer, so easily I can find it. So the transformation ratio will be A will be V2 by V1 by V2, that is 500 by 250, it will be equal to 2. Okay. Okay, now we'll do a problem, small problem. So the core of a two winding transformer, as we can see in this figure, is subjected to a magnetic flux variation as indicated in the below figure. So the flux variation in this core is like this. So it is given from 0 to 0.12. So the flux variation is happening, it is increasing linearly from 0 to 0.06, and then it is remaining constant from 0.06 to 0.1. Then again it is linearly decreasing from 0.1 to 0.12 second, right? Now we need to find what is the induced EMF in each winding. That means, so it is given, we need to find EAB, induced EMF across AB, A to B, and induced EMF across CD will be how much? ECD, right? So here you can see the terminals are marked with B and A here and C and D here, right? That means when the current will, the flux is in this direction, that means current is flowing in this direction, right? That means the the induced EMF, whatever it will be induced here, it will oppose the cause, oppose the flow of current, right? That means your actual induced EMF should be this, but we need to find in opposite way EAB. That means voltage with respect to A terminal, voltage of A terminal with respect to B terminal, right? So then how to find this? So okay, so before that, let us find the equation for flux. So equation for flux will be in the linear region if we'll, because the points are given here, we have 2 points of this line, we can find using the slope formula, we can find phi will be 0.15 t. Okay, and similarly if we'll find here, the formula will be, the equation for phi will be minus 0.45 t over, right? Okay. Now how to find this voltage? So EBA will be N d phi by dt, right? Okay. So EBA, I and I can write this EAB will be minus N d phi by dt, right? Okay. So your EAB will be minus N d phi by dt. So if I'll take the derivative of this, it will be 0.15 and N is 200. So I can write 0.15 into 200, right? So it is around 30. So it is around 300, sorry, 300 volt. Okay. Okay. So that is, so your EBA will be 300 volt plus 300 volt. Okay. Now similarly you can find it is from t equal to 0 to, so 0 to 0.06. Okay. And similarly, your ECD will be nd phi by dt. It will be minus 0.45 into 500. So whatever it will come, you can write it. Similarly, from t equal to 0.06 to 1, 0.06 to 0.1. So your EAB will be equal to 0. It is constant. The flux linkage is constant. And ECD will also become 0. Similarly, for t equal to 0.1 to 0.12, right? So it will be you can find, oh, sorry, this will be 0.15. Okay, so it will be around 750 volt. Okay, and here for 0.1 to 0.12 it will be EAB will be minus 0.45 into 200. Okay, is around 900 volt. And similarly ECD will be sorry, this will be plus, and ECD will be minus 0.45 into 500. Okay, this will be plus. So you can multiply this and you can find the answer. Okay. So this is the way we find the induced EMF. So if it is a sinusoidal waveform, then we can accordingly we can find the equation of the voltage, right? Induced EMF, right? So this is a simple problem. Now we'll talk about the non-ideal transformer. So what is non-ideal transformer? That means a practical transformer we are going to consider. So step by step we'll induce the non-ideality in the transformer. So the first non-ideality is your resistance. If we'll see any conductor you take and you make a coil, whatever may be, it has certain resistance. So we cannot neglect the resistance. It may be very less, but it has certain value, right? So therefore, so now we'll introduce the resistance of the two windings. So let us say R1 is your resistance of the primary winding and R2 is the resistance of your secondary winding. Okay. Now the voltage V1 is connected across primary side and it will induce an EMF certainly. So if the resistance is introduced, that means this transformer will incur some losses. So therefore now with the introduction of the winding resistances, the apparent power across the transformer, that is input power, will not be equal to the output power, right? It will be not equal because there is some loss. Okay, so therefore it will never be equal. now obviously we should consider the leakage flux in the transformer. So the leakage flux you can see here in this figure. For the whatever may be the coupling of the transformer, there will be certain leakage flux, right? And this leakage flux indicates that whatever the mutual flux, that is the flux linking between coil 1 and 2, is always less than the flux produced by the primary winding. That means your mutual flux will always be less than, let us say, the phi 1 is the flux produced by the primary winding. So therefore it will be always less than phi 1, and I can write phi 1 equal to phi m plus phi L1, that is leakage flux in the primary winding. So leakage flux will be in the air, right? So that means the leakage flux will leakage flux is a quantity which is not linked to the primary secondary winding, that is leaking to the air. Okay. Similarly, when the load is connected at the secondary side, when the current I2 will flow in the circuit, whatever flux will be produced here in the secondary side will also doesn't have any impact on this phi on this primary winding, right? Okay. So that leakage flux will not have impact on primary winding. Therefore, I can write phi 2 will be equal to phi m plus phi L2. I'm sorry. So phi 2 is flux which is opposing to phi m, and I can write it here phi m equal to phi 2. Under ideal condition, I can write this phi m equal to phi m equal to phi 2. Now one leakage component if we'll add, this will become phi L2. Okay. Okay, so your phi L2 will not have an impact on phi 1, right? Okay. So now if we'll see the these flux leakages, whatever is happening in the primary side and the secondary side, it will have an impact because whatever EMF was supposed to induced here in the primary side when the current I1 is flowing, because of this leakage flux, that much of induced EMF will not be produced in the primary side, right? So that means there will be a drop because of this leakage flux, right? So that drop I can write in terms of XL1, right? That means this reactance will indicate that this will represent in practically we cannot see this, but when we are modeling a transformer, we can represent the leakage flux, right? Leakage flux drop. So that means practically we cannot see a leakage reactance in the transformer. But when we are modeling a transformer, we can always represent the drop due to the leakage flux as an reactance, right? So because when we put a reactance, when the current flows, that will give a drop, right? So when I'll multiply Ji XL1, it will give a drop because the current is flowing. So therefore, the drop due to the leakage flux can be represented through this JIXL1, JI1XL1, right? So now therefore this is known as leakage reactance in the primary winding. Leakage reactance in the primary winding. Similarly, in the secondary side also, whatever voltage will be induced here, E2, will not be transferred to V2 because of this leakage reactance, because of this leakage flux. So therefore there will be a drop. So therefore I can write XL2 is representation of the leakage flux drop, the drop due to the leakage flux in the secondary winding, right? Drop due to the leakage flux in the secondary winding. Okay, so now I can write this XL2 as the leakage reactance in the secondary side. Okay. So this is how we represent. Now, if I'll represent R1 and R2, this we can see the leakage flux is represented like an inductance here, right? But practically you cannot see, like resistance practically you can see or you can measure, but this leakage reactance you will not practically, you cannot see. You cannot visualize practically. This is just a modeling aspect of the transformer. We are modeling the drop due to the leakage flux as XL1, XL2 in the primary and secondary side respectively. Okay. So now I can represent this leakage flux, which is represented as inductance here in the transformer. Now I can represent this as R1 JX1. It is mentioned X1, or you can also say XL1, but here it is X1 is mentioned, means we'll take X1. Okay, so let us say X1 and X2. Okay, so mark it X1 and X2. So now your transformer equivalent circuit, or your transformer model, will look like this. You can see here how it looks. Finally it is looking like this when you are considering the resistance of the winding and the leakage reactance of the winding, right? So both sides will have one resistance which will represent the resistance of the winding, and X1 in the primary side will represent the leakage reactance drop due to leakage reactance in the primary side. Similarly, your X2 will represent the drop due to the leakage flux in the secondary side, and R2 will represent the resistance of the secondary coil, secondary winding, right? Okay, so this is how it represents. Now, till now, we have considered only resistance of the winding, then the leakage flux or leakage reactance of the winding, right? But another thing we have not considered it, that is called, we are assuming still the core is having infinite permeability. That means the permeability, there is no reluctance in the magnetic path. Okay, so the reluctance of the magnetic path we're still assuming here as 0. When this reluctance will have certain value, certain finite value, then obviously this core will not have infinite permeability, and hence it will incur some loss, magnetic loss. And because of that magnetic loss, we'll represent this in the later slides, future slides. I will show it again. So just now you see what are the non-idealities we have introduced. One is your resistance, leakage reactance in both the windings, primary and secondary windings. That's all. So now, considering these non-idealities, till now we are not considering the non-ideality in the core. We're assuming this core is ideal core having infinite permeability. Okay. So considering this, if we'll write the terminal voltage equations, how it will look like. So obviously your E1 by E2, that is induced EMF, E1 by E2 will become equal to I2 by I1, that is nothing but equal to N1 by N2, right? So it will be equal to A, that is the transformation ratio. Now if I'll write the voltage, terminal voltage of both the side of the transformer, this E1 and E2 are the induced EMF, and V1, V2 are the terminal voltages, right? So now if I'll write the terminal voltage of V1 and V2, then V1 obviously I can write it is nothing but E1 plus R1 plus JX1 I1, right? So this is your induced EMF. So I can write V1, well, here you can write V1 will be equal to I1, current I1 is flowing in this. So I1 R1 plus JX1 I1 will give me V1. Similarly, if I'll write by applying KVL in this in the secondary side, if I'll write the equation for V2, V2 will be nothing but E2 minus R2 plus JX2 I2, right? Just apply KVL, you can find the equation, right? And this equation are based on the non-idealities in the windings. We have not considered the non-idealities in the core, right? Okay. So now let us do a small problem on this, where we are assuming that the core is having infinite permeability. That means the core is ideal, but the windings are non-ideal, right? So we're assuming the resistance and certain resistance and reactances, leakage reactances are there in the winding. So we can see here a transformer that is having rating of 23 kVA. This is your apparent power given, right? And the voltage ratings are given to 2300 volt and 230 volt. So when these voltages are given, you should know that these are the ratings of the terminal voltages, not the induced EMF, right? So these are the rating of the terminal voltages. Now the transformer is operating at 60 Hertz. It is a step down transformer. So step down transformer means the source is connected to the high voltage side, that is the source is connected at 2300 volt, right? And it has following parameters: the resistance and the leakage reactance. At the primary side, the resistance is 4 ohm. Secondary side, it is 0.04 ohm. And primary side leakage reactance is 12 ohm. Secondary side leakage reactance is 0.12 ohm. So the transformer is operating at 75% of its rated load. So what is the rated load? Rated load is 23 kVA. Okay. And it is operating at 75% of the rated load. That means 0.75 into 23 kVA, right? And if the power factor of the load is 0.866, this power factor is given, it is leading. That means there is a capacitive load. Determine the efficiency of the transformer. So find the efficiency of the transformer. So in order to find the efficiency of the transformer, we must know the P out and P in. That means output power and input power. So output power we know here, that is 75% of the rated output. So your output power is nothing but it is 0.75 into 23 kVA. Okay. And how to find this P in? Input power, if I know the voltage and current in the input side, then I can just multiply, I'll find, and the voltage and the angle between V1 I1, let us say, is theta 1. So I can write it as V1 I1 cos theta 1. Okay, that will give me the input power. Now after finding, so output power you know, after finding the input power you can find the efficiency. So for input, to calculate the input power, we need to know V1 I1 theta 1. V1 we know, that is 2300, right? And we need to find I1 and theta 1. So how we'll find? Let us see. So we'll start our calculation from the load side and let us find the current I2. So I2 will be nothing but if I'll divide it with the apparent power with the rated voltage, I'll find 75 ampere. Okay. So just dividing this and multiplying this 0.75 because the the operating load is 0.75, right? So I can find it this way. Now the I2 under 0.75% rated load is 75 ampere, right? Now what will be the angle of I2? I need to know. So before writing this, I need to find the impedance at the secondary side. This impedance of the secondary side is R2 plus JX2. Okay. So R2 plus JX2. R2 is given 0.04 and X2 is given 0.12. So your J2 in the secondary side is 0.12, right? 0.04 plus J of 0.12. Now with the knowledge of this, I know V2. V2 is given 230 volt, right? So if I'll take this voltage as reference, 230, right? So if I'll take this as reference, I can find E2, the induced EMF in the secondary side. So induced EMF in the secondary side will be V2 plus I2 Z2. So V2 is given 230 volt plus the current is, now the current is I2. So I2 is because the load angle is given, because the power factor is given here 0.866. So I can find the load angle, right? So that is theta 2 will be cos inverse of 0.866. So that will give me 30 degree, right? So therefore I can write I2 is lagging V2 by 30 degree, right? The terminal voltage. The I2 is lagging V2 by 30. If I'll write V2 as phasor, the reference phasor, then I2 will be lagging by 30 degree. That is also load power factor, right? So load power factor is nothing but it is the angular difference between V2 and I2, load power factor angle, right? So that is cos inverse of 0.866. Okay, so now I2 I know I2 is 75 30 degree, and just by doing this calculation I will find E2. E2 is coming about 228.287 and angle is coming around 2.33 degree, right? So after finding E2 I can find E1 because I know the transformation ratio. The transformation ratio is 10 here, right? 2300 by 230, so it is 10 here. So I can find E1. E1 is nothing but AE2, right? So A is given 10 and E2 I know, so I can find E1, right? And hence I can know I1 also. I1 also will be I2 by A, right? So I2 by A, that means it will become 7.5 angle 30 degree, right? So I know E1, I1, right? Now can I find V1, because V1 is nothing but it is E1 plus I1 into R1 plus JX1. So Z1 I know, Z1 is R1 plus JX1, that is 4 plus J1, J12 ohm. So now I can write V1 equal to E1 plus I1 Z1. So just by calculating it, so you need to do the complex calculation. So therefore, your calculator must have this capability to do this. Please remember, you must have a calculator which can do the complex calculations. Okay. So then we found V1 will be equal to this, right? It is coming around 2266.578. Angle is 4.7 degree. Okay. So now what is the angle between V1 and I1? So I1 is making an angle of 30 degree with reference and V1 is making an angle of 4.7 degree, right? So the angular difference between V1 and I1 will be how much? It will be, so uh, PO I can find it because PO is nothing but real of apparent power. So apparent power is 75 VA, right? Because at 0.75 we are finding, so it will be 75 VA. So if I'll multiply this 75, or just by multiplying V to I2, the real of this I can take, right? So whatever way you can find, okay, any way you can, just by taking 75 VA and multiplying the power factor angle, you will find this PO, because this is the real power. So it will be V to I2 cos theta. Theta 2, that is nothing but the real part of V2 I2 star, right? So that will give me 14,938.94 watt. Now I know the output power. Also in other way you can find this, you can check it. This output power I can find it as 75 because the VA is given as you can write it as 75. Sorry, you can also directly write 23 kVA, 23 into 1000 into load angle is, so the percentage load is 75% into 0.75 into 0.866. So it will also give me around 14,938.94 watt. Okay. So it will also give me the same answer. So in this way also you can find output power, right? Okay. So both way you can find the output power. Now we'll find the input power. So what will be the input power? Input power will be nothing but real of V1 I1 star, right? That means real part of V1 I1 star. V1 I1 star is the complex power. Now just multiplying V1 I1, I can find real part of this, or else otherwise you can write V1 I1 cos of theta 1, and theta 1 is nothing but, what is theta 1? Theta 1 is 30 degree. Here the angle is 30 degree and I1 is having 30 degree and 4.7, so it will be 30 minus 4.7. Okay, so this is the angular difference between V1 and I1, so I can write V1 I1 cos theta 1. The same answer you will get. You will get 15,389.14. Either way you can do, because this is a complex calculation. It will take more time. You have to find, you have to multiply again. You have to find the real part. Directly, if you find the angle, you just multiply V1 I1 cos theta 1. Directly you can find the power input, right? So now you can find the efficiency. So the efficiency is nothing but P out by P in, right, into 100. So that will give me, this is PO by P in, that is giving me around 0.971. And if you multiply it by 100, it will give me in percentage. So in percentage, the efficiency is becoming 97.1%. Okay. So I hope everybody understood this problem, simple problem. Here actually the non-ideality of the core is not considered. Okay, only we are considering the non-ideality in the winding, and we found this efficiency, right? Okay. Now, if we'll consider the finite permeability, what will happen in case of a transformer? So if your permeability is finite, then obviously your phi, the component of current, right, that is the magnet that produces the magnetic flux in the core, it will have two components. One component which will produce the mutual flux that we call Im, and other component which will provide the core loss. Okay, so the current which is now withdrawn under this condition for the core to produce the flux will have two components. One is having the component which produces the mutual flux and the other component which provides the core loss component, right? So therefore I can write this current IC as equal to E1 by RC1, right? So if I can represent the core loss component through a resistance RC, right? Suppose this is across shear winding, and if the current is flowing here, right, and E1 is the induced voltage across this, now I can write this component which is providing the core loss, I can write E1 by RC1, right? Okay. Similarly, the component which is providing the current component which is providing the magnetic flux, right, it will be completely inductive because it is providing the flux. So therefore I can write Im will be equal to E1 by J of xm1. So from this equation also we can write xm1 will be equal to E1 by Jim, right? Okay. So now we can, so we'll talk more in detail in the next class because your time is going to be over. So just I'm showing you, you can see it, and next class we'll again discuss this part. Okay. So now your core, non-ideality in the core can be represented through two components. One is RC1 and other one is XM1. So XM1 in fact represents the component which is producing the mutual flux, and RC1 is the resistance which is representing the core loss. Okay, so these are all fictitious, and we are using this in order to model the equivalent circuit of the transformer. That means all kinds of analysis we can do through these equivalent analysis. Any kind of steady state analysis in the transformer we can do through this equivalent circuit method. Okay, therefore we are just representing the core loss component, because the core loss means it is a loss component, so the heat will be produced right in that. So that means therefore it can be represented through a resistance, right? So therefore the core loss component is represented through RC1, and another component which produces the magnetic flux. It is only produces flux. It has no loss component. So that means it produces flux means it is clear that this component is purely inductive, right? So therefore I can represent the component which is representing the mutual flux. I can say this can be represented as a inductive component, and hence it is represented as xm1, right? Okay, so now your equivalent circuit is almost complete. All the non-idealities we have considered. One is R1, X1. R1 represents the winding resistance, X1 represents the uh, leakage reactance, and RC1 represents the core loss component. So core loss is having two components. Okay, one is your hysteresis loss, and other component is your eddy current loss, right? And similarly, your this xm is representing the mutual flux produced and which is enclosed in this core, right? And x2 represents the leakage flux in the secondary winding, and R2 represents the resistance of the secondary winding. And what is this part? This part will represent the ideal transformer. Okay, now all the non-idealities we are segregating, right, to different sides, primary side and secondary side, and this part will represent the one ideal transformer, right? So this part will function always as an ideal transformer. Okay, up to this part, from this part to this part, right? So if we'll give here some input is E1, so that means E1 I1 will be equal to E2 I2, whereas V1 I1 is not equal to V2 I2. Okay, so now we'll stop here, and maybe we'll talk later in the future, in the next class or in the next lecture. Okay, so we'll stop here. Thank you very much. Thanks a lot.